In this section, we'll be looking at rational functions and their corresponding graphs. So, rational function is nothing more than whenever you have a polynomial divided by a polynomial. And remember, a polynomial could be a constant or some expression of a variable, typically x, to some integer exponent. I have some examples of polynomial functions down here, f of x, g of x, and h of x. In each case, we just have a polynomial divided by a polynomial. Now, since it's a fraction, you automatically know that rational functions will have a restricted domain, because in any fraction you can never allow the denominator to be 0. So that's what I'm saying here, is that they always have a domain restriction. Any value of x that causes the denominator to be 0 has to be excluded. Now, if I look at the examples that I have above and I ask you to state their domain, you'd say, well, for f of x, you know x minus 4 is not going to be able to be 0, or that fraction could not exist. Well, if x minus 4 cannot equal 0, then I know x cannot equal 4. Now, automatically, the domain is what values x can be. So I'd say the domain is from negative infinity to 4, union from 4 to infinity. Now for the second one, if I'm thinking about the domain of that expression, I'd say yet again, I just say that denominator cannot equal 0. Now what I've done to set the denominator not equal to 0 is I went ahead and factored it here. I said factors of negative 10 that sum to get to positive 3. Well, that's a positive 5 and a negative 2. I know 5 times negative 2 is negative 10. 5 plus negative 2 sums to get the plus 3x in there. Now, if I set each of those factors, remember, not equal to 0, neither one of these factors could equal 0, or that fraction does not exist. Excuse me. I know if the first factor is equal to 0, then x would equal negative 5. My negative sign is small there, but that's x cannot equal negative 5. The second factor cannot equal 0 means x cannot equal positive 2. So if x cannot equal positive 2 nor negative 5, then that sets up a domain for our function. X can equal any value from negative infinity to negative 5, union any value from negative 5 to 2, and then again union any value beyond 2, so from 2 to infinity. The last one here, I don't really even have to worry about it. And you think about why. Remember, a polynomial exists everywhere as long as the denominator is not 0. Well, this one's going to exist everywhere in the real number system then, because x squared, you can square any number in existence and add a 6 to it. You're not getting a 0, so it has a minimum value of 6. So you'd say, since that denominator cannot be 0, that polynomial h of x exists everywhere. Now, when we talk about vertical asymptotes are going to be where the graph has a x value that cannot exist in the function, and typically your graph is going to approach infinity or negative infinity as you approach that vertical asymptote. Well, vertical asymptotes are going to be on these values of x that cause the domain restrictions, as long as the value that causes the domain restriction doesn't algebraically simplify in your polynomial. Let me show you what I mean about that. So vertical asymptote is a vertical line where a graph is going to jump from either positive or negative infinity in the y direction. It could also be a literal hole in the graph. So the first example I want to look at here is when we have this hole in the graph. If I graphed out the function k of x is equal to x squared minus 1 over x minus 1, you know that that numerator could factor by difference of 2 squares to x plus 1, x minus 1. Well, then that factor of x minus 1 in the numerator could cancel with the factor of x minus 1 in the denominator. And you would say the very value of x that causes k to not exist, namely at x equals 1, cancels with that numerator. And so you say, well, then k of x is just the graph of x plus 1. Now, it is the graph of x plus 1, except it doesn't exist at 0. But anytime that factor cancels out, your function's not going to be going from negative to positive infinity. You just have a hole in the graph at that point. Now, let me go ahead and show you this one on the calculator here. If I were to graph this rational function in here, I'll tell my calculator to do a fraction there, and then I'll say x squared minus 1 over x minus 1. And I'll go zoom decimal, zoom 4. This will be a good zoom screen for this graph. Now, notice what happens at x equals 1. At x equals 1, the left and right hand side are both going to the same value, and it's certainly not going up towards infinity or negative infinity. It looks like a nice line. So this is saying, hey, this is just a graph of y equals x plus 1, with the exception at y equals x plus 1, when x is 1, your y value would be 2. If you hit trace x equals 1, your y value here is undefined. This function does not exist at 1. However, it should be approaching the y value of 2 as x approaches 1, because if this were just the function x plus 1, when x is equal to 1, the y value would be 2. Well, notice if I hit trace and I choose a value just to the left of 2, like 1.999, just to the left of 1. I'll clear that out and go 0.999. The y value should be very, very close to 2. And you see, well, yeah, it is. And the closer I get to 1, the closer that y value is going to get to 2. Same thing would happen on the other side. If I went 1.01, my y value is 2.01. The smaller the difference I make between 1 and the value I plug in, the closer my y value gets to 2. So I can see, yeah, okay, no matter how close I get on the left or right hand side, that y value is just approaching 2, even though the function does not exist at 1. There's an open circle at the point in that graph. Okay, now, next page here. So we don't always have asymptotes, but we normally do. Most of the time, you're not going to have that algebraic simplification possible in your problem. You're going to need to go ahead and think of where the asymptotes are at. So let me show you some examples where we would have to think of asymptotes. So the vertical asymptotes come directly from the domain exclusions, as long as those domain exclusions factors do not cancel with the numerator. So that's you should always try to find the domain exclusions before listing vertical asymptotes. Now, in this problem, again, because I need to be concerned about if factors in the numerator and denominator cancel, if I give you an expression like this and I'm asking you for the vertical asymptotes, you think, well, okay, first of all, let's find the domain restrictions. You would find that by factoring the denominator. Factors of -6 that sum to get to -1. You'd say, well, that's -3 and a +2. So my denominator factor is to be x minus 3, x plus 2. That numerator, I know that 2x squared had to be 2x times x. And I knew that the only factors of -1 are -1 and +1. My middle number had to have a coefficient of +1, so I knew the +1 had to be opposite the 2x. So this would give me 2x squared plus 2x minus 1x for a total of plus 1x, and then I'd have my minus 1 there. The nice thing about this is I see, well, none of the factors in the denominator cancel with the numerator, so both of those domain restrictions would lead to vertical asymptotes in this case. So I had a factor of x minus 3, which meant x could not equal 3, and I had a factor of x plus 2 in the denominator, which meant x could not equal -2. Those domain restrictions lead directly to vertical asymptotes. I will have a vertical asymptote at -2 and 3 on this function. Now, in terms of vertical asymptotes in the second one, there are none. And this is just like the problem I had on the first page, where you say, well, the denominator can never equal 0, so there's no domain restrictions. Well, x squared plus 9 cannot equal 0 either. No domain restrictions, no vertical asymptotes. And then in my last one here, your numerator would factor to be x plus 3, x minus 3. Neither of those would cancel with a factor of x plus 2 in the denominator. So you'd say, well, your domain restriction is x plus 2 cannot equal 0, which means x cannot equal -2. This would only have a vertical asymptote at x equals -2. Now, when we talk about the horizontal or slant asymptotes, so we've already talked about the vertical asymptotes up here. the other type of asymptotes that talk about what happens to our function as x approaches infinity or negative infinity. Well, you look at that by just looking at the degree of the numerator over the denominator, and you're going to have three cases that come into play. You're going to have horizontal asymptotes in the first two cases, and you'll have a slant asymptote in the third cases. I forgot to label the third case here. Let me go ahead and put that in. This is case 3. So your first two cases, if the numerator's degree is less than the denominator's degree, well, y equals 0 is going to serve as your horizontal asymptote. So, the reason you need to think about that, if your numerator, its degree is less than your denominator, like this problem right here, if x got large in this problem, you know your denominator is going to be way larger than your numerator. Let's say even at 1,000,000, your numerator would be 1,000,000 plus 5. Well, that's minuscule in comparison to your denominator, which would be 1,000,000 squared plus 9. So at x equals 1,000,000, the size of your denominator is essentially 1,000,000 times larger than your numerator, which means your fraction goes off towards 0. Every single solitary time, if the degree of the denominator is greater than the numerator, your horizontal asymptote is going to be y equals 0. And again, it's simply because your fraction gets small as x gets large. Now in the second case, if the numerator and denominator have the exact same degree, you're going to have a horizontal asymptote at y equals whatever the numerator's leading coefficient is divided by the denominator's leading coefficient. I put an example over here to show you what this is referencing here. So if I had the polynomial 5x squared minus 3x plus 2 over 7x squared minus 9, all I would need to do is recognize, hey, the degree of the numerator and denominator is the same. So where is my horizontal asymptote going to be? It's going to be at y equals, and I just say the fraction of the leading coefficients. And the leading coefficient numerator is 5, denominator 7. That problem will approach 5/7 as x goes to infinity or negative infinity. Now the other scenario, well, what if the numerator's degree is greater than the denominator's degree? And in that case, you're not going to have a horizontal asymptote. So no horizontal asymptote. Instead, you would have what's called a slanted asymptote or a slant asymptote. And we're going to find those slanted asymptotes by, you can either use long division or synthetic division. But when you do that, you're always going to ignore whatever the remainder is. And I have an example of this on some coming pages here. Okay, now, next page here. If I talk about the end behavior of these functions and I want us to state our answer in form of the horizontal lines equation or the slanted lines equation. Okay. So in all of these problems, I'm wanting us just to state what the horizontal asymptotes would be. So f of x is equal to 2x plus 1 over x plus 3. I look and I can say, well, the degree of the numerator and denominator is the same. Every single time that's the case, your horizontal asymptote is going to be at y equals the fraction of the leading coefficients, which in this case is 2 over 1 or y equals 2. Your next problem here, you have g of x is equal to x plus 1 over x squared minus 16. Automatically, you should say, hey, that falls back to rule 1. The degree of the denominator is greater than the numerator every single solitary time that's the case. Y equals 0 is your horizontal asymptote. Now the last one, this is our case 3 from the previous page. So when I'm looking at this one, I can say, well, now I know that the degree of the numerator is greater than the denominator. Every time that happens, I'm going to have to use either long division or synthetic division to find out what the slant asymptote is. So x squared over x, I said numerator's greater degree. I need to divide that x plus 2 into the x squared plus 9. X goes into x squared x times x plus 2 gave me x squared plus 2x. I subtract that out. X squareds cancel. And then I would have minus 2x plus 9 brought down. X goes into minus 2x, negative 2 times. So I get negative 2 times x is negative 2x. Negative 2 times 2 is minus 4. Then I subtract that out. The 2x's cancel. But I would have 9 minus a negative 4 is 13. That 13 is really irrelevant. That's your remainder. X will no longer divide into that. So please just remember, your slant asymptote is what happens when you divide the denominator into the numerator and you ignore the remainder. So you ignore the remainder for the slant asymptote. So our slant asymptote here would just be y equals x minus 2. Simple as that. Now, let's go ahead, do everything that we've just done, but in combination with that, graph out a function. So here I'm wanting us to look at the function f of x is equal to x minus 3 over x squared minus 3x minus 4. If you're going to do a problem like this, then it really does help to go ahead and factor that denominator. It factors to be x minus 4x plus 1. Neither of those factors simplify with the numerator, so I know both of those factors, not only are they domain restrictions, or they cause domain restrictions, but they also cause vertical asymptotes. So my domain restrictions, x minus 4 cannot equal 0, x plus 1 cannot equal 0, gives me x cannot equal 4, x cannot equal negative 1. I go ahead and set up my domain. X can be any number from negative infinity to negative 1. Then any number in between negative 1 and 4, and then union any number after 4, so from 4 to infinity there. Now, the vertical asymptote, you just say neither of the factors that caused a domain restriction canceled with the numerator, so both of those lead to a vertical asymptote. I will have a vertical asymptote at x equals 4. I will have a vertical asymptote at x equals negative 1. The function cannot equal those values, so it's going to go off towards infinity or negative infinity as x approaches those values. Now, when I'm talking about the types of whether it has a horizontal or slant asymptote, and notice capital or there, it's one or the other, never both. It's impossible to have both a slant asymptote and a horizontal asymptote. I look at the original problem, I can say, well, this is an easy case. Degree of the numerator is 1, degree of the denominator is 2. Every single time the degree of the denominator is greater than the numerator, you have a horizontal asymptote at y equals 0. Now, before you start worrying about the graph, you really should go ahead and do all of this work beforehand. So I'll say, okay, yes, I've found my horizontal asymptote at y equals 0. I know there is no slant asymptote. What about x-intercepts? You just take your original equation, or you'll see I took the factored version of that original equation, and you say x-intercepts occur when y is equal to 0. So I just set my original equation equal to 0. And if a fraction is equal to 0, the only way a fraction can equal 0 is if the numerator equals 0. So you really only need to say set the numerator of the fraction equal to 0. That's going to give you x equals 3. So I know I have an x-intercept at the ordered pair 3, 0. Now for the y-intercepts, again, I take that exact same equation, I did the unfactored form here, and the y-intercepts occur when x is 0. So you'll see I plugged in f of 0 is equal to 0 minus 3 over 0 squared minus 3 times 0 minus 4. That's where this comes from. And then you say, well, that's just going to give you negative 3 over negative 4. And then that simplifies down to 3/4. I know I have a y-intercept at 3/4, which means the coordinate, y-intercept always occurs at when x is 0. I have a coordinate 0, 3/4 for the y-intercept. Now I go to my graph. I plot both my x-intercept and my y-intercept. My x-intercept at the ordered pair 3, 0. My y-intercept at the ordered pair 0, 3/4. You would also go ahead and plot your two vertical your vertical asymptotes, a vertical asymptote at x equals negative 1 and a vertical asymptote at x equals 4. Those vertical asymptotes should always be drawn with dashed lines. Now it's kind of hard to show the horizontal asymptote here because it's right on top of the x-axis. Y equals 0 is the x-axis, but what I tried to do is show a dashed green line right on top of the x-axis there. And all that means as x approaches infinity or negative infinity, the y values must approach that horizontal asymptote. Okay, now you cannot pass a vertical asymptote ever. It's an undefined value of your function. Alright, so whenever I started graphing out this function, I started in the mid portion. I said, okay, you've got your x-intercept, you've got your y-intercept. You know that those have to be connected. As soon as I connected those two, and you know you can't have any other x-intercepts, so, and also this x-intercept, it came from a factor degree 1, which means it must cross. It's not just going to touch and go back in the direction it came from. So I knew it came down, crossed through at x equals 3, and then it's going to approach that asymptote towards negative infinity. When I go off in the other direction, I know that the function must go up towards positive infinity. Again, it can't miraculously come down and cross here because there's never another x-intercept. So you say, okay, it's got to go up in that direction. Now, anytime the asymptotes that you have come from a factor degree 1, then there's always going to be opposite behavior on one side of the asymptote to the other. So the asymptote that generated 4, or the factor that generated the asymptote at negative 1 was degree 1. The factor that generated the asymptote at 4, also degree 1. All that means, guys, is that you're going to have opposite behavior on each side of the asymptote. So if this side goes down, the other side's going to go up, and then instantly I know, well, as x goes to infinity, the y value must approach that horizontal asymptote. Same thing over here. We already knew the shape in the middle, and so then there's no doubt on the other side of that asymptote at x equals negative 1, it had to approach negative infinity. And then as x moves to the left, this function is going to approach the horizontal asymptote. It's not going to cross the horizontal asymptote. It's going to approach the horizontal asymptote towards 0. So I could say as x approaches negative infinity, the y value would approach 0, but it's always going to be a slightly negative value, so you never hit 0. You just approach 0 from values below 0. Gorgeous graph there. Now, could you plug in a value to the right of 4 if you wanted, or to the left of negative 1? You certainly could. There's no need to, though, guys. Once you understand the properties of rational functions, you should be able to draw this in without plotting points in this region or this region. You should just be able to get it from your x and y intercepts. Now, up next, if I'm looking at the graph of 2x squared over x squared minus 9. So automatically my denominator factors to be x minus 3, x plus 3. Both of those are going to generate domain restrictions at positive and negative 3. So my domain is going to be negative infinity to negative 3, union negative 3 to 3, union any number from 3 to infinity. Now, I know the vertical asymptotes, since neither of these factors that cause the domain restriction, you can't cancel out either one of them algebraically. So I know that they both do lead to vertical asymptotes. I'll have a vertical asymptote at negative 3. I'll have a vertical asymptote at 3. Now when I'm thinking, well, what's the horizontal asymptote? Horizontal asymptote, our rule for that is you look at the degree of the numerator and denominator, they're the same. So anytime they're the same, the horizontal asymptote is going to be at y equals the fraction of the leading coefficients. That's going to be 2 over 1. So you'll see, I didn't circle it, I should have. This only has a horizontal asymptote, and the equation of that horizontal asymptote is going to be y equals 2. Now, the x-intercepts here, you say every single time, if a fraction is equal to 0, the only thing that can cause the fraction to equal 0 is the numerator. So when I try to solve for the x-intercepts, notice all I've done is I said set the fraction equal to 0. It's when y is 0 for the x-intercepts. That's just going to be when 2x squared is equal to 0, and I'll have x equal to 0. Now, keep in mind here, don't just say, oh, okay, you have an x-intercept at 0. Remember, that's a double root. It was x squared equals 0, which means it will not cross the function at 0. It only touches at 0 and goes back in whatever direction it came from. Okay, now, the y-intercepts here. The y-intercepts, and instantly, as soon as I know the x-intercept is at 0, I also know the y-intercept. But in general, to find the y-intercept, you evaluate your function at when x is 0. But notice when you try to plug that in, you're just going to get y equals 0. And I already knew that. If it's crossing the x-axis at 0, then it crosses the y-axis at 0 too. So you have the ordered pair 0, 0 for both of them. Now, I go ahead and I plot that x and y-intercept, and I also plot all of my asymptotes. So ignore the rest of the function for me for just a minute. I plotted that x-intercept there. I plotted my vertical asymptote at x equals -3. I plotted my vertical asymptote at x equals +3. I tried to plot a horizontal asymptote at 2. That's supposed to be a completely horizontal line there. Mine's accidentally slanted a bit, but remember the equation of that is just y equals 2. Now, as soon as I plotted this point, I can say, okay, how am I supposed to know it goes down? Do I need my graphing calculator to help? Absolutely not, guys. Use the asymptotes to help guide the graph. If you were thinking, well, how do I know it doesn't go up like this? You're not going to cross that horizontal asymptote like that. So I know as soon as I hit that x-intercept, and I can say, okay, it's a double root, so it only touches. Well, it's going to touch at x equals 0, and it's going to go down on both sides and approach those asymptotes. Now, I can say, well, how do I know what it looks like on the other side? It's always opposite behavior on the other side of the asymptote anytime the factor that caused the asymptote is degree 1, which both of these are degree 1. So I can say, well, if I'm going towards -infinity as I approach 3 on the left, I better be going towards +infinity as I approach 3 on the right. Then what's going to happen as x gets large? Well, as x gets large, your function's going to come down and approach the horizontal asymptote of 2. Same thing happens on the other side. You can say, well, on the other side of -3, we know that as x approaches -3 on the right-hand side, it's approaching -infinity. So as you approach -3 on the left-hand side, it better be approaching +infinity. So I can say, okay, I have that drawn in, and then I know as x approaches -infinity, the y value better come down and approach this horizontal asymptote of 2. And that's how we would graph out this rational function. Now, I'm not saying you can't ever use your calculator to assist with these graphs, but you really shouldn't need to. We should be beyond having to depend upon our calculator for these problems. The beauty and the relationships you can do without any calculator assistance whatsoever. Same thing happens on this one. A lot of students would struggle with this one. They usually have a lot more trouble with the slant asymptotes. So first of all, you recognize this will not have a horizontal asymptote, but a slant asymptote instead, because the degree of the numerator exceeds that of the denominator. Now, we'll get to that in a minute. Let's talk about our domain restrictions. Domain restriction, if I tried to factor the numerator, factors of -4 that sum to get to +3, I said, well, that's going to be +4 and -1. So I said the numerator factors to be x plus 4, x minus 1. Neither of those factors cancel with the factor in the denominator. Either way, I still have the domain restriction that x cannot equal -2. So I know that x can be any number from -infinity to 2, and then from any number from 2 to infinity. Okay, the vertical asymptote will occur at 2 because I'm not just going to have an open circle at 2, it's going to actually be a vertical asymptote because that factor did not cancel with anything in the numerator. Vertical asymptote at the domain restriction. Now, in this case, I already discussed this at the beginning of the problem, we will not have a horizontal asymptote because the denominator is of greater degree. So what I went ahead and did here to find the equation of the slant asymptote, please notice I used long division. I said, well, sorry, not long division. I used synthetic division. I said if x minus 2 is a factor in the denominator, then the solution there would be x equals 2. I would synthetically divide with a synthetic divisor of 2 into coefficients of 1, 3, and -4. That's what I did right here, synthetically divide with 2 into coefficients 1, 3, and -4. The 1 came down. I said 2 times 1 is 2. 3 plus 2 is 5. 2 times 5 is 10. -4 plus 10 gave me a remainder of 6. Now remember, the slant asymptote is always y equals the equation, and you ignore the remainder. Our numerator was degree 2, our denominator was degree 1, so this answer is degree 1. This is trying to tell you that your answer is x plus 5, and it would be plus 6 divided by x minus 2. We ignore the remainder though, so you just say, y equals 1x plus 5. That is our slant asymptote here. Now before I worry about the graph, I need to think about my intercepts. X-intercept is always when you set your equation equal to 0. When this equation is equal to 0, it's the numerator that would equal 0. That's going to give us two solutions. You're going to have an x-intercept at -4, and you're going to have an x-intercept at +1. So I know I have coordinates -4, 0, and 1, 0 here. And then lastly, the y-intercepts, you said, well, the y-intercepts occur when x is equal to 0. Well, when is x equal to 0? I can say, well, when x is equal to 0, the y value is going to be -4 over -2. And I can say -4 over -2 is going to simplify to be +2. So the y-intercept is going to be the ordered pair 0, 2. So before I started connecting any curves and stuff in here, the first thing I did was I graphed the asymptotes. I knew I had a vertical asymptote at x equals 2. I drew it in with a dashed line there. And then I knew I had a slant asymptote at the at the diagonal equation, y equals x plus 5. You should know very well how to graph that. Y equals mx plus b. You say, well, it's just in that line with a y-intercept of 5, 1, 2, 3, 4, 5, and a slope of 1. So since it had a slope of 1, what I did is I said, I can't draw an x-intercept over here, but I could over here. If it has a slope of 1, if I move down 5, I better move left 5. So I knew it crossed the x-axis at -5 if it crossed the y-axis at +5, since it had a slope of 1. So I kind of just drew in my line using those 2 points, and then I said, okay, that line's going to continue forever and ever and ever at that same slope. So now I have my two asymptote equations drawn out. Then I started plotting my x and y-intercepts. I had x-intercepts at -1, at +1 and at -4, and then at 0, 2 for my y value here. Okay, now I know that I needed to connect those points in there, and then automatically that helped guide my graph, because I can say, well, okay, I connect those points in there. What's going to happen as I move further to the left? Well, you can't just abruptly cross that slant asymptote. It doesn't work that way. But what happens as x gets further and further and further to the left, it's going to get closer and closer and closer to that slant asymptote. So that's what I tried to show there. Same thing on this side. As I approach that vertical asymptote, so as x gets infinitesimally close to 2, it can never equal 2, but I know that the y values in this case are going to go off towards -infinity. On the other side of the vertical asymptote, I know that anytime the vertical asymptote is from a degree 1 factor, you have opposite behavior. So if you were thinking, well, how do I know it doesn't go down here? Because that would be the same behavior as this. It had to approach +infinity as x approaches 2 on the right. So I went ahead and did that up here, and I said, well, it has to approach +infinity as x approaches 2 on the right. It's going to come down. You cannot cross either the vertical or the slant asymptote, so that allowed me to draw in this function up here. As x approaches infinity, the y value is just going to get closer and closer and closer to this equation at y equals x plus 5, and that's what I tried to show there. Now, if you followed me on these, you should be really good with graphing these rational functions. And again, I'm not saying you cannot ever use your calculator to aid. I'm just saying it really shouldn't be necessary most of the time. Most of these problems we can do just out on our own if we have a good understanding of the rules of this section.